We're going to spend some time exploring data structures. The book, unfortunately, has a nice exposition of two of the most basic ones and doesn't go into as much detail about the classes that are available in Java that give a very rich set of data structures that you can use out of the box. In days past, in a class like this, basically the students would have to build these data structures based on linked lists, doubly linked lists, queues, stacks, all those sorts of things. Today, in today's environment, you just need to know about them and be able to use the ones that are available. It's important to know a little bit about what's going on under the hood, and I'll be showing you some examples of why that's important. Even for something like a list, it's crucial to use the appropriate data structure for the task that you're doing. Otherwise, you could make your application just woefully slow. And in more computer science-y type of classes, they get into the big O analysis. I don't know if you've ever encountered that. Yeah, so and that's important. It's important to understand that to a certain degree. Yeah, okay, yeah. Those are important things to understand, and in this context, use them to understand which data structure to use for a particular application. So, I like the term collection. Data structure sounds kind of fancy, but basically collection just means that you have this object that's going to contain other objects. And that's basically what a collection is. And different ways of storing those things and different rules for storing them and getting stuff out of them, that's what makes the difference. We're going to just basically focus on lists and sets. And then after that, next week, we'll talk about another important one called maps. Now, the collections in Java are so-called generic, and we've encountered that when we've seen array lists, where we define array lists by telling it what we need to put in it. And this is different from what you may have encountered in either Python or JavaScript, where what they call arrays are actually, in fact, like these array lists. They certainly differ from Java arrays in that Java arrays are just very, very rigid in that they can contain a certain number of items and that's it. So if you know how many items are going to go into your collection, your container, then an array is the appropriate data structure to use. If you don't know how many, and you want to keep them in some kind of indexed order, then some kind of list is appropriate. And we'll see two types of lists as we see. So, in particular, there is an interface called list. And we've talked about what an interface is. And there are two main implementations of that in Java. One is array list, which we've encountered, and the other is linked list. Now, you all know what a linked list is, and the book talks about how that's organized. And you've encountered that before. So you know how it's under the hood. The difference is this. An array list stores its data actually in an array under the hood. You don't need to remember that so specifically, but then knowing that, you might wonder, well, wait a minute, I can keep putting stuff into array lists and to no end, and it'll keep expanding in order to accommodate the new items that I put in. So how is that possible with an array? We've already done something like that. If you remember, there was an example we had where if we were trying to put more things in an array than it had been allocated, then what we did was we created a new array that was bigger and then copied all the elements of the old array into the new one. You remember that? That's basically what an array list does under the hood. And so you don't have to worry about it because it does all that for you. But it's important to understand that that array is what's backing the array list. Whereas a linked list is implemented, and actually the linked list is actually a double linked list, as it turns out. So in the old days, the distinction between a single linked list and a double linked list were things that people fussed about. Java, by the time Java came around, they realized, well, let's just make everything a double linked list, because even if we only need the single part, then the extra stuff for double is not a big overhead. But a linked list is implemented, kind of as you understand a linked list to be. That is, instead of an array, they have these internal objects called nodes, and you have a reference to the first one, and then a reference to each succeeding one. So each node points to the next guy and the next guy and the next guy. Kind of like the Washington addresses his troops in Valley Forge and says, I've got good news and bad news. And the good news is we have a change of underwear. And the bad news is that you change with him and you change. So with a linked list, it's like everybody's pointing to the next one. That has implication. So these are kind of abstractions, and you don't need to remember the abstract part, but the key concept here is that they separate the interface of the object from its underlying implementation. The implication of that is that when we define the variables that will form our lists or sets, then it is ideal to define them as abstractly as possible. In other words, if I have a list, even if I know I'm going to use, say, an array list or a linked list in particular, I want to define the variable as a type of list rather than the specific one. We'll see an example of that. And what that does is that gives you the ability to more easily change from one to the other. Now, this abstract data type is this is a computer science-y term. Have you encountered that term before? No. Basically, just think of it as, I prefer the term collection, so never mind for that. So here's how a simplified version of the Java collections framework. It's a little more complicated than that, but this is really all you need to know. It starts with an interface called collection. And that interface of collection says that every collection must have certain methods. So that's how interfaces work, and we all know that now. So every collection must tell you how big it is by the size, and it must give you the ability to add something. Now notice that it doesn't have, and there are other things, but those are two of the most important ones. Notice that it There are specific ones, and again, as an interface, it simply defines these as abstract methods. And so a list interface extends the collections interface. So every list is a collection, but the list is still an interface. And there are two concrete implementations of the list interface that we will be interested in. One is array list, which we've seen already, and the other is linked list, which we'll talk about in a moment. And so what this sort of Java-esque UML diagram indicates is that in the collection interface, these are abstract methods. In array list and linked list, these are implemented as concrete methods, so that array list and linked list can be instantiated, whereas list can be defined as a variable type, but not instantiated. Now, the set interface has two direct implementing classes. One is called the hash set, which is the go-to one if you don't care about other stuff. There's one called the linked hash set, which does some things that we'll talk about. And really, one of the more important ones is another sub-interface called sorted set, of which there's a single implementation called tree set. The sorted set is a collection that keeps its contents in sorted order according to the compare to method of the containing objects. And as a consequence, a sorted set, and by implication the one implementation tree set, can only contain objects that implement the comparable interface. Basically, the tree set uses a rather fancy data structure called a red-black tree. You don't need to know that, but there are many different tree structures. The book mentions these tree things. These trees are some of the best ways of storing sorted items. So instead of trying to sort them by figuring out exactly what the order is, tree sets are just these fancy ways of doing it. And the red-black tree is one of the more sophisticated ones. And you don't need to know the details of that other than the fact that what a tree set does. So again, like what we're doing, and this is consistent with the way a lot of programming works in today's age, where we're one step removed from the bare metal a little bit. Okay, so the list interface. So how does it do stuff? Well, add, for all lists, it appends to the end. It expands if necessary. And again, how does it do it? Depends on whether it's an array list or a linked list. Again, as a user, you don't need to know that unless you're worried about exactly how you're going to use it. Now, one thing a list can do, like an array, is that you can reference a particular item by index, we can insert an item by index, or we can remove items by index. In other words, if I want to say, insert this value at the 5th index, it'll put it in the 5th index and it'll make everybody to the right of it, take one step to the right. If I remove something, say at the 15th index, assuming that there's room, then it takes it out, and then everybody with a higher index has to take one step to the left. This is kind of one of the key differences between lists and sets. Lists can contain duplicates. Whereas sets, which we'll talk about maybe in a bit, maybe tomorrow, cannot contain duplicates. And what defines a duplicate? Well, that can be a little bit of a subtle thing. Okay, so array lists that I said are like arrays. We can add in constant time, meaning if I want to add something, then on average it takes me a constant time, like ignoring whether we have to expand the array or not, because that's going to take a little bit of extra work. But what it does is very similar to what I had you do in one of the assignments. That is, it has an array which is typically bigger than the number of items that are in it, and it has an internal integer that's pointing to the next thing. And so when you go to add something, assuming that there's room in it, it simply puts it in the array at that index and then clicks the index up. Now, you can remove, this is where the difference comes. We can remove from the head in linear time. Okay, what does that mean? Like, let's say I have an array list, and I want to remove the first element. Well, what does it have to do? Well, when I remove the first element, everybody with a higher index has to take one step to the left. And that's, when you say linear time, that's going to be linear in the number of items that I have in the array list. So as the array list grows, the time it takes to do that is going to grow linearly. Whereas a linked list, again, now since you know how a linked list works, we can add or remove from the head or the tail in constant time. You know why? Because if I want to remove for the head, then there's a reference to the first item. You just basically have to kind of change that reference to the first item to the second item, or you have to fuss if it's empty then. And then just update a fixed number of these references, and that's going to be constant no matter how many. If I have 1,000,000 items, and I want to remove the first one, it's going to take me just as long as if I have 10 or 1. Okay, that may sound a little on the abstract side, but type of data structure, which is the set. Now, the difference between a set and a list is right up front. A set cannot contain duplicates. So a set is analogous to a mathematical set. Remember in your math classes, and I hope that doesn't impart too much trauma, but in math classes they talked about a set. So if you had a set of the integers from 1 to 5, you wouldn't have 2 3s in there. There would just be 1 3. So the implication is that a set can only contain unique items. And as I think I should have some time to try one out with some strings. So the add will only add the item if it's not already in the set. So if I go to add an item that's already in the set, it won't add it. There's no concept of an index. So in other words, I can't say, give me the 4th element. Just like in a mathematical set, I can't say, give me the 4th element of the set. There's no such thing. It's just a bag of things. So you can think of a set as just a bag of unique items. There are 2 types of these things, and each has their place. One is called a hash set, and that is the most common. That for sets, that's kind of the go-to, because the order, when I say arbitrary, the order is based on something happening internally called a hashing function. Have you heard that term before? It's not important to know the details of it, other than the fact that it's just a way of computing a unique number for each object. And internally, Java has that But as if we're using a hash set for one of our custom classes, and we'll see tomorrow when we try to use a hash set for our playing card that we have to create a hash code for those playing cards. Otherwise, we're going to get duplicate elements. The other set is called a linked hash set. And like a set, it has no duplicates, but what it does is it keeps things in the order that you put them in. And that's sort of the difference. So if that matters, if the order that you put them in matters, then a linked hash set is what can do that. Whereas a hash set is, we say, arbitrary order. The order is determined by this thing called